Hello, in this lecture we are going to introduce the backpropagation algorithm, which is a widely used algorithm for computing gradients of neural networks. The first step to train a neural network is to define a loss function, representing how well our neural network is doing on a dataset. For instance, in the case of classification, you can use the cross entropy, while for regression, you can use the square loss. In both cases, in order to use algorithms such as gradient descent or one of its variants to find the best parameters, weight of biases of the neural network minimizing the loss, the key step is to compute the gradient of the loss with regards to the parameters of the neural network. The backpropagation algorithm allows one to compute such gradients efficiently, and it's one of the reasons of the success of neural networks. To understand the backpropagation algorithm, let's start from the chain rule. The chain rule is one of the standard rules to compute the derivatives of composite functions. Intuitively, if as in the first example in the slide, we have that y is given by a composition of f and g, then the derivative of f with respect to x is given by the derivative of f with respect to g times the derivative of g with respect to x. This rule can of course be straightforwardly extended to composition of more than two functions and to vector or matrices, as shown in the slide. As we will see, the chain rule is one of the key components of the backpropagation algorithm. The other key component is the computation graph of a composite function, which is a directing acyclic graph representing the composition of the function. In the composite graph, each node is an operational variable. Essentially, the intermediate nodes of the graph represent arithmetic operations involving the child nodes. As building the computational graph is intuitive, let's try to better understand this process with an example. We consider function y equal to w1x1 plus w2x2 squared. Let's start with internal operation, in this case w1 times x1 and w2 times x2. As x1 and w1 are elementary units, those are elementary units, scalar or variables, and this defines the leaves of the graph. Any operation between these units give rise to the parent nodes. The parent nodes are then summed, and finally the result is squared. The importance of the computation graph is that it's helpful to guide the chain rule. In particular, first we compute the derivative of each node with respect to each child nodes in the graph. This derivative I've written in red for the previous example. For instance, in the case of y, its only child is z1, so that is the only derivative we need to compute. Then, if we want to compute a given partial derivative, it is enough to simply travel the graph backwards from the root to the variable with which respect we want to compute the derivative to. Then, you multiply the partial derivatives you find. For instance, to compute the partial derivative of y with respect to x1, just navigate the graph backwards from y to x1 and multiply the partial derivatives. We obtain the results written in red in bottom right corner, 2 z1 w1. Note that if a variable appears more than once in the graph, there may be multiple paths to consider. For instance, in the modified graph in the slide, now there are two paths from the root that lead to x1, and we need to sum them. We then obtain 2 z1 w1 plus 2 z1 w2. We are now ready to introduce the backpropagation algorithm. The first step is to build the computation graph of a neural network. Then we do a forward pass through the network to evaluate the graph on the current inputs and parameter values. Then, once we have done that, we do a backward pass from the root to compute the derivatives of the output, the root, with respect to all the parameters. It is important to stress now why the backpropagation algorithm is so important in neural networks. It allows one to compute the gradient of the output of the neural networks with respect to all the parameters at once, with just a forward and a backward pass of the network. Thus, it has a time and memory complexity which is linear in the number of neurons. Such an efficient algorithm is one of the keys that allows us to train large neural networks with millions of parameters.